In section 11.2, sorry about that, we were able to generate power series representation of functions, but everything we were doing came down to relating it to 1 over 1 minus x in some way. So it involved derivatives, it involved combinations, it involved nesting one function inside another, aka composition, and sometimes a mixing of those, so taking an integral and a composition at the same time. So we need a way that's going to work for a more general process. We've got a lot of other functions that will not work with relating it to 1 over 1 minus x's series. So to that end, we are going to introduce Taylor and Maclaurin series. So let's assume the function f of x does in fact have some kind of power series representation about x equals a. So in other words, you have a coefficient plus another coefficient times x minus a, plus another coefficient times x minus a squared, and so on and so on and so on. That's a power series. It's centered at x equals a because you can see that a is in every piece of, well, every term of the power series. All right, next assume that the following, or excuse me, that the function f of x has derivatives of every order that we could find all of them. So for example, let's start off with the first one. So f of a would mean that we put a into this function. So if you put a in everywhere, this term is going to disappear because a minus a is 0. This term is going to disappear, so a minus a is 0, and so on. So the only thing that won't disappear is c0. Now let's find the derivative of f of x. So if f of x is equal to this lovely power series that goes on forever, then we should be able to find f prime of x. So f prime, the derivative of the constant, is 0. So that first term disappears. The derivative of this piece, well, that's to the 1 power, right? So we would bring the 1 down, and it'd be c1 times x minus a to the 0, but x minus a to the 0 will go away, so we don't have to worry about that. Plus, now bring that power down, so it's 2c2, and then it'd be x minus a to the 1, plus 3c3 x minus a squared, plus 4c4 x minus a cubed, and so on and so on and so on. All right, now what would that derivative be at a? Well, all of the terms are going to disappear that have x minus a in them, and the only term that's going to be left is the constant, which is c1. All right, next, the second derivative. Well, I'm going to take the derivative of the first derivative, which will make the c1 part disappear, but then I'll have a 2c2. So 2c2, x minus a will go to the 0, plus, and then a 6c3, x minus a to the 1, plus a 12c4, x minus a to the 2. And actually, let me just throw in another one here. It would be 5c5, x minus a to the 4th, right? So that would give me a 20c5, x minus a to the 3rd, right? Let me just note real quickly. This is 3 times 2. This is 4 times 3. Well, 3 times 2 times 1. This is 4 times 3, right? Then this is 5 times 4. Well, I guess the 1 won't really matter for what I'm doing. Never mind. Interesting. Seems like there's a relationship going on. Oh, I remembered. I wanted this one to be 2 times 1. Okay, so notice what's going on here. You have 2c2, but I can tell there's a little bit of a pattern going on. I'll be back for that pattern. All right, let's keep going on to the next page. And I want the third derivative. So I want the derivative of this piece. Well, this part's going to go away, and then I'm going to have 6c3, and then x minus a will go to the 0, so that's not relevant. And then I'm going to have 12 times 2, which is 24. Actually, I'm just going to write it. 4 times 3 times 2, c4 times x minus a, which we all know is 24. But I'm trying to shoot for a pattern here. And then the next one would be, Well, 5 times 4 times 3. So it'll be 5 times 4 times 3, which we all know is 60. C5 x minus a squared. And then following that same pattern, you can imagine how the next one's going to go. There would have been, well, let's see here. This one would have had a 30 C6 x minus a to the fourth, because it would have been 5 times 4 would have been 6 times 5. So down here for the next derivative, it'll be 6 times 5 times 4 C6 x minus a to the fifth plus dot dot dot. Oop, plus dot dot dot, because it just keeps continuing on like that. This is better known as 120. Okay, so then if I put a into that, then all these terms are going to disappear except for that first one, which is 6, which is 6c3, or if we like to know it as 3 times 2 times 1, c3. Interesting. All right, now the fourth derivative, remember when it's in parentheses, that's another derivative. That would be, well, let's see, 4 times 3 times 2. So 24c4, aka 4 times 3 times 2 times 1, 4. Oh, I'm doing the next part. Sorry about that. All right, so hold on. I was gonna do it down here. So this one's 24c4, which is 4 times 3 times 2 times 1 c4. But I'll keep going. So 24c4, and then I would bring this 2 down, so it'll be 5 times 4 times 3 times 2 c5 x minus a, right to the 1. And then the next term, oh, that was a third there, sorry. That was supposed to be a cube. All right, so that would be 6 times 5 times 4 times 3 c6 x minus a squared. And it would continue on like that. So obviously I'm shooting for a pattern here. There's something going on, right? Which is that there's a pattern to these coefficients. So this one's 4 times 3 times 2 times 1 c4. This one's 3 times 2 times 1 c3. If I go back, 2 is 2 times 1 c2, right there. And then this is 1 c1. And you might think, oh, it doesn't have that pattern here. Oh, but it does. The pattern, 4 times 3 times 2 times 1 is 4 factorial. 3 times 2 times 1 is 3 factorial. So 4 factorial, 3 factorial. And then this is 2 factorial. This is 1 factorial. And actually, here, this is 1 also, but 1 is 0 factorial, right? For a wide variety of reasons, not least of which is that we define it that way. So that means that f to the kth derivative would be, let me write it down. So if you look at the pattern, the kth derivative at a, which are these ones that we're finding, these secondary ones, is always equal to k factorial times ck. Interesting. And that means that ck, the coefficient, must be equal to the kth derivative at a divided by k factorial. And we can use that fact to define our Taylor series. So a Taylor series, if we suppose we have a function f that has derivatives of all orders on an interval containing the point a, the Taylor series for that function f centered at a is this power series where you can see the coefficients are the derivatives divided by the factorial, right? And that's what they're saying right here. you take your kth derivative, you divide it by k factorial. And so that's right here, right here. Those are both ones, so that's where that is. Then it's right here, and so on. Right, so this is 0 factorial, this is 1 factorial, but they're both 1, so they're kind of, minor points. Now, Maclaurin series is the Taylor series, but centered at 0. So it makes it a little bit simpler because it doesn't have all these parentheses there. It's just x instead of x minus a. It's just x squared instead of x minus a squared. It's just x cubed instead of x minus a cubed. So Maclaurin series is just a special kind of Taylor series with a center at 0, which you can imagine is a little bit easier to work with generally than a Taylor series that has a center that's not 0.